Hello everybody, my name is Debela. I'm PhD student at Silesia University of Technology, Poland, and University of Stavanger, Norway. And it is my pleasure to attend on this conference. And today I want to talk or give highlight about the mechanical property of form, specifically the tensile property of 3D form, subject to uniaxial tensile load. As introductory part, we know that form is a class of several solid structures. So several solid structure is a class of material which have a porosity in its structure. And this porosity is always usually greater than 70% of structure is porous, and this porosity makes a material lightweight, energy efficient, and sustainable materials. This several solid is a very common material or interesting material for automotive and aerospace industry in present day due to this play important role in reduce fuel consumption and greenhouse gas emission. As we see from this figure, the common application of this solids is in aerial vehicle wing structure, in helicopter component, pneumatic tires, cylinder head, and orthopedic implant, also rib structure. So when we compare this solid structure with true solid materials, and for criteria, the first one is density, strength, Young's modulus, and conductivity. This density is much lower than that of true solids, and this property makes it very interesting material for lightweight application. And the second one is it is strength. If you see from the graph, the strength of this form is much lower than that of true solids or bulky materials. And this one is the challenge, or the main challenge of this material, and this makes it is a barrier to use this material for application which needs a higher strength. So the researcher also working in this area in order to improve this tensile or as well as compressive strength. And sometimes they use some additives like graphene or other nanomaterials, nanoparticles. So, but still now the strength of this material is not improved very well. So this area, on this area, the researcher is working in the present day. Regarding to Young's modulus, the same is true here. It is Young's modulus also much lower than that of true solids. Even it is Young's modulus is much lower than that of elastomer. So the other one is this conductivity. This thermal conductivity also lower than that of true solids. But in this area, the researcher is the many work is worked in order to improve this thermal conductivity, like using carbon forms. This property is highly improved. So nowadays, researcher, especially materials science, is working in order to improve this strength. So as a research gap, when we come up to our focus today, as a research gap, if you are familiar in this area, there are plenty of materials published about in order to investigate the compressive property of this form. There are plenty of papers published, But regarding to tensile property, there are very little paper is published in this area. It looks like there is when we say this published paper, it looks like this form is not subject to tensile load. But if you say sandwich structures, this is subject to the compression load as well as tensile. So there is a gap in order to investigate the tensile property of form subject to the uniaxial tensile load. So the main challenge in order to investigate these tensile properties, if you see as you see from this diagram, the end of this sample is full of there is plenty of incomplete edge. So this makes it difficult to attach this one into universal testing machine. So it needs special designed grips in order to investigate this tensile property. So the other one is brittle forms such as ceramic and carbon form is highly brittle, so it is not easy to attach or to test this tensile property, so which result is very low strain. So we come up to objectives. The main objective of this paper is in order to investigate the effect of pore density and the solvents on ultimate tensile strength as well as on elastic modulus. So we used 3 pore densities, that is 20, 40, 60 ppi, that means pores per inch. Here, well, in order to make clear what is 20, 40, and 60 ppi, the first figure A is 60 ppi. That means if we draw a line which is 1 inch, this line passes through 60 pores. The same is true for the 40 ppi. If we draw 1 inch length line, approximately pass through 40 pores, and for 20 also the same. Okay, here this slide tells us about the sample preparation stage. We used the polyurethane foam as a template, and we covered this polyurethane foam by a solution of phenolformaldehyde and alcohols, different alcohols, which is methanol, acetone, and ethanol. And the purpose of using this phenolformaldehyde to cover this polyurethane foam is due to this polyurethane foam is it easily burns if when we put this foam into dryer or in furnace. So we cover with this phenolformaldehyde. And the other one, the purpose of using those alcohols, ethanol, methanol, and acetone, is as we know, the viscosity of this phenolformaldehyde is high, so it is not easy to pour or to immerse this to uniformly distribute this phenolformaldehyde into these forms, especially for higher pore density like 60 ppi. So we dissolve this phenolformaldehyde by those alcohols, then we can easily immerse this polyurethane foam into the solution of those phenolformaldehyde and the alcohols. And the other one is if the higher viscosity of this phenolformaldehyde results to block the cell wall of the foam, which results in non-uniform distribution of cells. Okay, now we come up to the tensile test setup here. we designed this here. We designed a special grip in order to attach these forms to it. And as I said before, the main problem in order to get to perform the tensile test on this form is due to this incomplete edge at both ends. It is very difficult to perform this tensile test. So we designed this special grip. It looks like this one. After that, we apply here, we apply epoxy here, and we attach the specimen to this special design grip. After that, we attach here. There is in this side we have a universal testing machine. So after performing the tensile test, we get such like arrangement. That means there is a fracture of specimen here, and generally this tensile test is performed on universal testing machine with a capacity of 2.5 kilonewton and at the room temperature with the loading rate of 0.5 millimeter per minute. Here, when come up to the tensile test stress strain diagram here, if you see this figure, we performed 3 tests for first. We performed 3 tests in order to use it as average. Here, if we move from here to here, this one is a stress strain diagram for 20 ppi, this one is stress strain diagram for 40 ppi, this one is stress strain diagram for 60 ppi. So from this figure, it is easily observed that the ultimate tensile strength is increase as the pore density increase from 20 to 60. So if you see this stress strain diagram here on the first figure, it looks like smooth. But if we zoom out this stress strain diagram, there is a peak and a valley here. What does it mean? This peak and the valley means this valley indicates that the lowest, the weakest cell fell first, and it transferred to the second cell. After that, that second cell is also failed. That means the second cell is fails and transfer to load to the other cell, and after that, lastly, we get this fracture of the specimen. That means from this figure we can easily observe that all cell fail step by step. That means there is progressive crashing of cell rather than brittle fracture of all specimen. That means it fails step by step. Here, when we come up to ultimate tensile strength and the modulus from this bar chart, here the higher ultimate tensile strength is observed in 60 ppi, which is 477, and the lowest ultimate tensile strength is observed with a form with lower pore density. The reason behind why this ultimate tensile strength is higher for higher pore density is in higher pore density. That means in 60 ppi we have a lot of finer cells. That means a cell is fine. That means it close to uniform, not exactly uniform, but it is nearly uniform than that of 20 ppi and 40 ppi. And in addition to that, since it is 60 ppi, that means we have 60 cells per 1 inch. That means all cells contributes to resist this tensile load. The same is true for elastic modulus. This elastic modulus also, if there is finer cells, that means 60 ppi, the form is stiffer than that of 20 and 40 ppi. Regarding to solvents, here we have the lower tensile ultimate tensile strength is observed in acetone. That means when we cover with acetone, it shows lower ultimate tensile strength. That means there is lower bonding between this acetone and higher 60 ppi. There is a lower interfacial bond between acetone and these forms. When come up to statistical analysis, we perform the statistical analysis by using Origin Lab. And first we test the normality test on this data by using Shapiro. So from the result, we get the p-value here. So we get the p-value which is greater than 0.05. So this data is obeys the Shapiro normality test. So after that, it's possible to proceed the two-way ANOVA analysis. Here is a two-way ANOVA result. From this two-way ANOVA result, the p-value for pore density, solvent, and the interaction effect is less than 0.05. That means from this result, we can say easily pore density, solvent, and their interaction significantly affect both ultimate tensile strength and elastic modulus. Okay, lastly, when you come up to conclusion, form with higher pore density, 60 ppi, showed higher ultimate tensile strength as well as elastic modulus, and form with lower pore density shows lower ultimate tensile strength. And acetone treated form had the highest tensile strength, while methanol treated form showed higher elastic modulus. So this is all about my presentation, and if you have any question and a suggestion, welcome. Thank you.